Good afternoon. My name is Daniele Antuzi, and today I'm going to show you a project that we implemented for one of our customers. So we implemented an indexer implemented using the MapReduce paradigm and using the serverless infrastructure. So our client wants to move out from the usual server because they don't want to maintain Apache server. So they are trying to move everything to the serverless infrastructure, and we design this kind of MapReduce indexer. So before starting, a few words about myself. My name is Daniele Antuzi, as I said. I'm a software engineer. I got a master's degree back in 2014 at the University of Pisa. And I've been working in many fields like finance, cloud services. And 4 years ago, maybe, yeah, already 4 years ago, I joined Sease, where I worked for a few customers. By the way, let's see. Today, this one, sorry, guys. Today, we are going to see what the problem, one of the main problem of an indexer. So how we combine records from the database. Then we can see a short introduction about MapReduce, so we can have everybody on the same page. And then we can see how we can combine records in database using MapReduce. And finally, we can focus on the serverless implementation. Finally, we can see some results. So what's the problem? So normally, all data are stored in a relational database where all the information split in multiple tables. So and we don't want replication of data. So let's suppose we have a database where we want to index songs. So we have a table with songs. We have another table for composer, another table for albums, another for tags, for example. But when we want to index all our information, we want all this data in the same document. So, for example, let's suppose we have a document with ID, title, album name, album composer, and tags. All of them come from different tables. And what the problem is, how can we join all this information in a quick way? So, quickest solution ever and easiest solution. Big select where we join everything. That's the simplest solution, but what's the problem? The cardinality of the result can be huge. And this is not scalable at all because, and also there is too much work from the server side. So let's move forward. Let's try to make this solution more scalable. Let's say more or less. So we list all the songs, and for each song, we extract all the composer for that song, all the all the tags for that song, all the albums for that song. Let's say this is not a good solution because this can be slow as well, because for each query you have to send it to the web, to the database. The database is going to optimize it, create the plan, execute it, and return the result many times. So this is not another good solution, and we didn't go forward with this one. So as you can imagine, we proceed with MapReduce. What is MapReduce? MapReduce is a programming pattern to access and processing big data over a distributed file system. So this one has been introduced in 2004 by Google engineers, if I'm not mistaken. In this paper, simplified data processing on large cluster. The idea, what's the idea? The framework, there's a framework. The framework does take care about, I mean all the usual problems about communicate between nodes, where to find file, and so on. And the user only needs to define two functions. map and reduce. So let's see with an example. The hello world of MapReduce is the word count. So if you have to calculate the word count of just in a file, what do? You list all the words of a file. Maybe you keep a data structure as a map, as a dictionary, for example. And for each word you find, you increment the counter. That's easy. But how about if you have to calculate the word count for all pages in Wikipedia? Where the word, I don't know, quick is stored, in which pages, where these pages are stored, and where are the nodes where this page is stored. So there are many other problems we need to face. And that's why MapReduce is useful. So MapReduce execution is composed of multiple phases. So the first phase is we need to split our dataset. So in Wikipedia it's simple because the dataset, you can use each chunk of information. So a single page is a chunk of information. And each page is stored on a server, on a node of our cluster. So in this case, data are already split. So what do? In each node, we execute the map function. And we transform, given the file, what the map function does. We can create a list of key value, so that where the key is the word, and the value is the word count, I mean the cardinality, the number of occurrences of that word in that file. And this one can be executed in parallel in all nodes. Afterwards, the framework shuffles all the results and can combine together all the values with the same key. This is a really high level, so we don't need to, I mean, I'm not focusing on specific implementation or framework, I mean. So for example, in the node 1, we have the word Berlin with 5 occurrences. The result of the map on the node 2, we have Berlin with 1 occurrence. So we group together these 2 values. And finally, in the reduce, we combine together all the values we found. So we run in parallel all the reduce functions, getting the list of values coming from the previous step, and we find the result. Word count, we have the word count of many nodes already grouped together. We just need to sum them up. And we have our results. So how can we use MapReduce to work to combine database records? Let's come back to the original problem. We have our relational database. We have our songs with a song ID and track ID. We have albums with some attributes, tags, and composers. So first of all, we need to, as we say, the MapReduce group together all the value pair with the same key. So first of all, what is the key in this case? So we want to generate a document for each song. So the key in this case can be identify the key as a song ID. So what do? We get for each, first of all, we get the list of songs. The songs have the song ID. That's it. We can get the full list of songs. Then, for all other attributes, other tables, we combine and we join all tables that we need. So all information, for example, about the albums, and we join with other tables. Okay, this is a simplified model. We join with other tables to find the song ID. Same story with all tags, combined with the song ID, composer combined with the song ID. What do we have? We are going to have a result set with song ID and other values, possibly replicated multiple times. For example, if we say, maybe it's more for composer. There are two composers for the same that compose the same song. You will find the song ID two records with the same song ID, and the composer replicated multiple times. So the song ID and the composer. For albums, it's the opposite. The album information can be replicated multiple times, one time for each song ID. And that's what we want, because at the end, each replication of the album values is associated to the final document for that song ID. So we do it for all tables, or depending on the information we want. And this is what we get. Let's say we get a file of something in memory. Let's stay high level. We get a list of songs with all information about songs. We get the full list of albums and the song ID. So we had album name, maybe, I don't know, album title, descriptions, whatever, and the song ID. Same story for composers, for tags, for other values. So at this point, we run the map. The map does, given the song ID, using the song ID as a key, we generate a key value pair where the key is the song ID and the value is the title, the attribute name, and the value, album name and the value, composer name and the value, and that's it. And we generate this list of key value pairs. We can rely on our framework that combine everything, so does the shuffle, and I suppose it's a magic. When we write the reduce, we should find for each song ID, we find all the information grouped together. So we found the song ID and, I don't know, title, album name, composer, and so on. In this way, writing the reduce function and writing the document is so easy, because you don't need to search, okay, where is the title of this song? Where should I find the composer? Everything is there. You just need to go, copy, and create the document. And as I said before, all these reduce functions can go in parallel. So you can go extremely fast. Let's now see what we implemented and how we used the serverless infrastructure on AWS. So first of all, the ingredients. I forgot the quotes maybe. So we have a SQL database where all the information are stored. We used AWS Lambda function, that is service that allows you to run and execute a piece of code in one server. I don't care where the server is running, somewhere. But this code will be executed somewhere. I don't need to maintain those servers. I don't need to do anything else. We have an S3 bucket. So this is another service, probably almost everybody knows it, where you can store files. We used simple queue service, SQS. This is a queue with some other, the queue that can guarantee you the so when you store data, you don't lose this data. And there are other options we will see afterwards. We use DynamoDB is a key value database. It's pretty fast, and we can use this fast attribute, value for synchronization. We will see afterwards. And one of the main, the biggest service we use is AWS step function. And we used a new feature, okay, now it's implemented almost 2 years ago, is distributed map. It allows you to list all the files in an S3 bucket. And for each file, it triggers a Lambda function passing the file name and allows you to execute up to 10,000 Lambda function in parallel. So you can see you can process up to 10,000 S3 bucket files in parallel. And finally, we have Apache Solr, or by the way, we can use Elasticsearch, OpenSearch, our search engine. So that's the pipeline, the high-level pipeline. We have a function to fetch data from database and store them into an S3 bucket that we call input from database. Okay, it's zero fantasy, I know. When everything is done, we execute the map in parallel for all files, and we map them. Actually, this is, I'm cheating, let's say, because my map is map and shuffle together. It means, yeah, at the end, what do we have? We have a file for each, let's say, song ID, containing all the information about a specific song. Afterwards, we run the reduce, we process it, and the result goes in an SQS queue. We need it to decouple the merging phase, MapReduce phase, with the push into Solr phase, because this MapReduce can be extremely fast, and if you don't decouple it, risk to bombard your search engine. And finally, we push to our search engine, Solr in this case. So let's go in details. Let's go start with fetch. The fetch function execute all our queries. Okay, still using the same example. Let select all songs, title, and so on, and we get the list of songs. We don't write all of them in the same file, mostly for two reasons. Performance reason, and also keep the memory under control, because while I receive the record set from database, I can create a buffer. When the buffer is full, I start flushing them into an S3 bucket, an S3 file. So I don't need to, I don't know, maybe select 1 million files, 1 million record set, and then create the file. So in this way, I can maintain the memory under control, and it's even faster because while I download data from database, I start writing them. So it can go in parallel. Second reason is that if I split the source record set into multiple files, okay, let's suppose here we have only 3 select. If I create 3 files, then in the map phase, I can elaborate 3 files in parallel. If I create 3,000 files, I can go much faster in the second phase. So indeed, what the map does, the map reads, the map, say, and shuffle, read. Okay, first of all, process all files in parallel. For each file, start reading record by record and see, okay, song 13, let's create a file, doesn't exist yet, in another S3 bucket, song 13, and append that value, album name A. In this case, we can do a single write. We have album name A and B for song 13. What was the problem? As you can see here, there are 2 files, album and tags. Both of them have to process the song ID 15. Maybe these 2 files can be elaborated in parallel. So what it means, there's a concurrency problem we need to solve. We don't have POSIX, we don't have mallocs or semaphores, or I don't know, mutex. So we need to implement some solution. That's why DynamoDB was is really helpful because it is pretty quick and allows you to create an atomic put. So you can write a new record only after some specific condition. So what do? We create this table with resource ID. And in our case, it can be the ID of our song. Okay, lock ID can be, actually, it's not so important, let's say, and expire at. And this is the timestamp when our lock record is going to expire. This is important because we are in a distributed environment. Let's suppose we acquire the lock and we don't have this expire at. It means the Lambda function acquired the lock, it failed for some reason before releasing the lock. So this resource is going to be blocked forever. So that's why the expire at is important. So as you can imagine, to unlock one resource, the function goes there and delete the record. Let me come back because there is another optimization. When we request data from database, I require the database guy to provide all data sorted by the key. In our example, all data are sorted by song ID. This is important because when we write during the map phase, if the data sorted by song key, I can find all the songs, all the values with the same key in the same file. I mean, at least in the same file for album, maybe 2 files for albums, in the 1 or 2 files for tags, 1 or 2 files for composer, and so on. So when I write on S3 to the, let's say, final file, I don't need to write. I mean, there's going to be less read and write to S3. This is more, let's say, is it faster? And in S3, you pay for each read and write. So if you reduce, actually in my example, in my test, I reduced by 100 times, more or less. So 2 orders of magnitude. If you reduce by 2 orders of magnitude the number of read and write, you save money, many money. And second of all, also less Lambda function trying to access the same resource. You reduce the risk of having conflicts. I mean, they don't need to lock that resource. I mean, you need to lock, but there are no other functions try to acquire the same lock. I mean, you reduce this possibility. Okay, let's now go to the reduce. I don't have much to say now because the reduce now is pretty simple. We read from this bucket file, and in parallel, we find everything there. We just go create the document to push to Solr or whatever. I don't think there's something more to add. And finally, we need to push to Solr. There are 2 possible solutions. Having one Lambda function or something, one server, pulling from the queue. When there are data, create the batch and send it the batch, envelope, and send it to Solr. Another possibility is to push. So I don't want to have my Lambda function go and require and receive from the queue. I want the queue that when there are enough data, enough messages, create the batch and send it to the Lambda function. So actually, in SQS, there's the possibility to invoke a Lambda function when one batch size, there are enough messages. Okay, here there are my batch size is 2 messages, or if there is only 1 message or not enough messages, after a batch window, 60 seconds, start flashing the queue and still invoke the Lambda function with the messages you have. And afterwards, you can also decide concurrency, because there are plenty of messages in the queue. SQS can invoke a lot of functions in parallel, but more functions you invoke, more messages you send to your search engine. So you need to do some tuning, because the overall speed up of all your service or your indexing. But if you have too much, you need to look at the metrics of the search engine and see how it's behaved. And actually, we go ahead with this solution. Even simpler. We start with the simplest solution, and then, what did we achieve? This solution has been implemented, of course, not in this simple and high-level way. There are many other problems, but unfortunately, there's an NDA, and I cannot go too much in detail. By the way, we are in production since April, and we looking at some statistics, but we didn't need it, because the indexing time dropped from about 150 hours, 5 hours. And also costs were reduced. Actually, looking at the cost, we are comparing the cost of maintaining the servers, actually only buying servers. We didn't consider the cost of maintenance, the hour that the infrastructure team, DevOps, spend to patch them and maintain them, compared with the cost of the number of execution we need during the month.